We live in an incredible world today where we can use our smartphones and get all kinds of information, or we can sit at our desktops and play incredible games with other people in real time. It is a great, great time to be a tech. However, the CompTIA A+ really wants you to understand networking in a deep and profound way. So if you really want to understand networking well enough to be able to pass the A+ and to succeed as a technician out there, we've got to bring it down a little bit. Forget the smartphones, forget the fancy tablets, forget Google. Let's take it down to a simpler world. A time before the internet, a time when networking was really just for a few computers, maybe 5 computers, maybe 15, maybe 20 computers that worked together in the same office, that were all hooked together, and the only thing they shared back in the old days was they'd probably share a printer, and they'd probably share each other's folders so that we could access each other's Microsoft Word documents. So we're going back to a very, very simple time, very basic networking and what we call a local area network, or a LAN. So let's talk about that for a minute. So imagine I've got a nice little office here, and I've got some people with some computers and they're working away, and maybe there's somebody with a laptop over here, and here's a printer. And what we would do back in the old days, and still do today, is we would run wires, not between the computers, but to a central little box that, at least for the moment, I'm going to call a hub. So everybody is physically connected from this central point called, again, momentarily, we're going to call it a hub. Now, in today's society, it still works that way. In a wireless world, for example, we would have something called a wireless access point, and everybody's talking on the same frequency to that particular wireless access point. Well, that sounds okay, but right off the top, I see 2 big problems. Problem number 1, how do we keep any one person from hogging up the network? And problem number 2, how do we know how to send data to this computer and not that computer? Let's take a look. So imagine a situation where I've got Shannon and Dana who are all plugged together on this one local area network. Now, Dana wants to access Shannon's Microsoft Word document. Now, if she were to simply start grabbing that, anybody else who wanted to talk, let's say it's a huge document, he kind of hogs up everything, and that could be a real problem. So to keep anybody from hogging up the entire network, a bunch of folks got together back really in the late 1970s and developed a type of networking called Ethernet. Now, it may be old, but it is still the most popular type of networking that we use today. Ethernet defines what kind of cabling we use, what kind of these little hubs, it defines speeds, it defines all kinds of stuff, but it also defines something really important, and it says you can only make your data in discrete chunks of 1,500 bytes. So if you want to send data, for example, if you want to send a Microsoft Word document and it's 100 megabytes big, that'd be a big Word document, it has to be broken up into zillions of these little 1,500 byte chunks called a frame. Now don't worry, we'll see that the operating systems have the smarts to take the Word document apart and then put it back together on the other end, but for right now, a frame is only going to be 1,500 bytes tops. Well, that takes care of one problem, but it doesn't take care of another. So here's poor Dana over here, and she wants to go talk to the Shannon computer because she wants to get a hold of this Microsoft Word document. But there's lots of other computers on this network. We have to come up with some way to uniquely identify each computer on the network so that we know how to talk to these guys and not to the others. So what I've got set up in front of me is a very, very simple network. So here's one computer. Now, it used to be we had network cards you snap in, but they're all pretty much built into the motherboards today. So on this motherboard right here is a Ethernet connection. And as we go over to this other one, he's got an Ethernet connection as well. And they all come together in this central box, which I'm going to temporarily call a hub. In fact, there's even another computer I don't care about. He's somewhere else. So in this particular situation, I've got 3 computers. We uniquely identify every system on the local area network through something called a media access control, or MAC address. A MAC address is a 48-bit address, which is always manifested as 12 hexadecimal characters. So let's put up a MAC address right here. So this is an example of what a MAC address might look like. So every network card in the universe gets a unique MAC address. So if it's got 12 hexadecimal characters, the first 6 characters are what we call the OEM ID. So if I'm going to start making network cards, I am issued those first 6 characters from the issuing body of the internet, and then I can spin up all the other ones as much as I want. So these 2 computers in front of me have MAC on them. So what I'm going to do is, his MAC address is this, and this one's MAC address looks like that. Would you like to see the MAC addresses on your computers? It's easy. If you're on a Windows system, just open up a command prompt and type in the command ipconfig /all, A-L-L. If you type it, you're going to see something that looks like this. There's a lot in there, but there's one particular line I want you to concentrate on. You see where it says physical address? That's the actual MAC address for the network card in your computer. This also works with Mac as well as Linux systems, except you use the command ifconfig, or you could just use if, and you can get basically similar results. All right, so we now have MAC addresses that are assigned to every network card out there. So what I'm going to do now is I'm going to add to this frame. And what we're going to do, every time we send out a frame, instead of just the data, at the beginning we're going to put the destination MAC address and then the source MAC address. So actually I've got some MAC addresses in here already. So this will get it to the correct computer, and as a courtesy, we always put the source MAC address in case they want to talk back to us. They know our MAC address already. Now, as you take a look at this, there's only one other thing I want to add, and that is what we call a frame check sequence, or FCS. The frame check sequence is nothing more than a checker so that when this data gets over to its destination, they can compare this value to the data, and it gives them a pretty good idea as to whether the data came in good order. So what you're looking at here is the basics of what we call an Ethernet frame. These frames were invented almost 40 years ago, and we still use them on the highest speed networks out there today. What you may not be noticing is a term that people love to use a lot called IP address. IP addresses are important, but in a small local area network like this, they don't really do much. In order to appreciate IP addresses, we need to start making our networks bigger through something called a wide area network. I want to talk a minute about that little box that everybody connects to make a local area network. I've got a bunch of these little boxes in front of me. Some of them only have maybe 5 connections, some have more than that. It doesn't matter. One of the things that's important with these boxes is I can plug these network cables in anywhere I want. You don't have to plug them in certain points, but as long as all the computers are plugged into one of these little boxes together, I've got a local area network. But that's not the issue. What I want to talk about is there's 2 very different technologies in front of you. I've got 4 things called a switch and 1 thing called a hub. Now, I'm going to give it away. This box right over here on top is a hub. Now, underneath it is a switch. Can you tell the difference? Mike, we don't even know what the difference is yet. I know that's what this episode's all about. But I want you to look very, very closely. If you look on this top one right here, you'll see it says hub. And if you look at the lower one, you'll see it says switch. So what is the difference between a hub and a switch? Well, let me show you. Here on the left, I have an 8-port hub. And you can see I've got 4 computers, A through D. And what I'm going to do is I'm going to connect these computers to this hub. Now, it doesn't matter where you plug them in. As long as they're all connected, we now have a local area network. But something very interesting takes place. Let's say that computer D wants to talk to computer A. So computer D sends a frame, and it goes into this port right here. This box is what we call a repeater. It takes the signal that comes in and it repeats it. It makes a new copy. So it's not an amplifier. It repeats the signal and sends that signal back out where everybody is connected. So that way, everybody will get the conversation between D and A. Now, these other computers, they'll read the MAC address, and since they know their MAC address, and they look at the destination MAC, they just erase it because it's not for them, and that's how the communication goes. Now, there's a problem with this type of setup. Let's say that C and D are talking, and A and B are talking. On this hub, I'm going to say that it has a maximum throughput of 10 megabits per second. Now that sounds like a lot, but if you're trying to copy a Word document or send a printer job, it can actually be very slow. And we're going to make it worse because A and B are talking and C and D are talking. They're sharing that 10 megabits per second, which means both of these conversations are now 5 megabits per second. And heaven forbid we put 10 or 15 more computers on there, it really slows stuff down. So what I want to do is let's suddenly magically transform this hub into a switch. It looks the same, but it's going to act very differently. The first thing that happens is that this box will begin to collect MAC addresses. So as A plugs in, he'll write down the MAC address for A on a little internal list. As B plugs in, he now knows what the MAC address is for B, C, D, everybody who's on there, and it's all taken care of automatically. There's nothing to configure, and he now knows everybody's MAC address. By knowing that, something magical happens. Let's say A and B want to start talking to each other. As soon as the frame comes in here, the switch looks at the destination MAC address, because he's got them all memorized. He goes, oh, that's this port right here, and makes a direct physical connection, almost like those old-time telephone operators where they would plug into the switches. And the same thing for this communication right here between C and D. The power of this is that now, instead of having two 5 megabit per second conversations, we have two 10 megabit per second conversations because nobody's trying to talk over the other conversation. The bottom line is that switches work a lot better than hubs, so much so that I'm actually surprised that the term hub is still on the CompTIA exam. Nobody uses hubs anymore. We're in a world where it's nothing but switches, and I keep these around just to keep CompTIA happy when I need to talk about this stuff. So for the exam, make sure you know, number one, a hub is dumb. It just repeats back on all the ports whatever's coming out. A switch is still a repeater, but it's a smart repeater and only sends the data out to the proper destination based on the MAC address. If you're going to be making a local area network today, you're going to be using a switch. The computer world is full of binary, and it should be full of binary. Everything we do is wires going on and off, or storage areas going on and off. So 1 and 0 is the normal way that computers speak. And often we don't talk about just a 1 or a 0, but we talk about a width of them. Sometimes we talk about 32-bit CPUs or 64-bit CPUs, or sometimes we talk about 8-bit external data buses or 16-bit registers, or if you get into graphics cards, we have 256-bit memory. The important thing that all of these different chunks of 1s and 0s have is that they all have a least common denominator of 4. All of the numbers I just told you are divisible by 4. 8, 16, 32, 64, 128. And if we know that, we can actually do something kind of cool. Let me show you something over here on my computer. So I'm going to run a command called ipconfig, which we go over in great detail in other episodes. And I want you to take a look at this. All over the place, we see these numbering systems where we see zeros and ones, and then we also see letters of the alphabet. But notice that we never see a letter of the alphabet that goes beyond the letter F. It always stops at F. Well, what in the world is going on here? Well, the problem is, when we're talking about big long strings of ones and zeros, it's really hard for me as a human being to talk to another human being and saying, oh, well, the MAC address for my network card is 10010101011000011. You get the idea? It's really hard for us as human beings to talk in raw binary. So what we need is a shorthand, an easy way to talk about long strings of ones and zeros using something that makes it a little bit easier. So what we use is a nomenclature called hexadecimal. Now listen, hexadecimal is a complete base 16 numbering system. And in fact, if we had been born with 16 fingers instead of 10, this would be the normal way for us to count. However, it has some real benefits when you're dealing with big long strings of binary, and it has to do with how many different patterns you can have on 4 ones and zeros. Let's say I've got 4 ones and zeros. I don't really care what this is. This could be part of a MAC address. This could be part of a address coming through on my CPU. I don't really care what it is. This is just a nomenclature. So we could have all of the ones and zeros could be all zeros. That's one possibility. Then the first one or the last one could be turned on. Now I'm going to give you a clue right now. If there were a whole bunch of combinations, I wouldn't be trying to write them in real time for you. Okay, so what I've just done is I've written down every possible combination there is for a string of 4 binary values. Get the idea? So they could be all off, they could be all on, and a whole bunch of combinations in between. What we're going to do here is we're going to replace 4 characters with a single character. We're creating a shorthand nomenclature so it's a little bit easier to deal with long strings of ones and zeros. So here's the question. How many different combinations are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different combinations. What we're going to use is a base 16 counting system called hexadecimal to basically replace any 4 binary characters with a single character. Get the idea? So let's go ahead and do this. So anytime we have 4 zeros, we'll just replace it with a 0. Now that will put a little H at the end so you know it's a hexadecimal value. If we have this, we'll replace it with 1. I'm too lazy to write all the H's in there. 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait a minute, I can't write 10. The whole reason we're doing this is to replace all 4 binary combinations with a single character. So if I write 1, 0, somebody will think I meant 0, 0, 0, 1, 0, 0, 0, 0. Get the problem? So what we got to do is we got to replace it with 1 value. So what I propose we do is replace it with the letter A. And you're like, why A? Well, because somebody chose this a long time ago. I could put a smiley face in there if I wanted to. Doesn't matter as long as everybody agrees that this value represents 1010. Get the idea? So let's keep going down the line. I can represent any string of 4 ones and zeros with the numbers 0 through 9 and the letters A through F. Get the idea? So let's practice this. So what is this value in hexadecimal? So it's 1101, 1101. So this would equal DD in hexadecimal. Get the idea? And we always put the little H on there as a nice way to remind people that we're talking in hex and we're not talking like letters of the alphabet or something like that. So this, my friends, is hexadecimal. The whole goal behind hexadecimal is simply a way to prevent us from having to write in big long strings of ones and zeros and to compress that a lot into smaller values. Now that you know that, and this is important, every single hexadecimal value equals 4 binary values. So I'm going to have a question for you. We're going to take a look at something called a MAC address on my computer, which Windows calls it a physical address. I need to know how many bits long is this particular address. Let's go back over to the computer and take a look. So here's something called a physical address right here. Do you see that? And these are hexadecimal characters. See the letter C, that's our clue. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you have 12 hexadecimal characters and each hexadecimal character represents 4 binary values, that means that a MAC address is going to be 4 times 12 or a 48-bit address. Remember, hexadecimal is simply used as a shorthand for things like us human beings to represent long strings of binary values. I'm not saying it's a perfect representation, but we get to write 1/4 as many things on the screen, and for me, that makes hexadecimal worth it. What I got in front of me is what we call a 24-port switch. Now, these switches are based on a standard called Ethernet, which we've been using for ages and ages. Ethernet is absolutely amazing. It works incredibly well. Our Ethernet frames send data back and forth in our LAN using the MAC addresses. Everything's fantastic, as long as you keep it relatively small. So if I'm using this switch, the most computers I could put on one local area network would be 24. Well, there actually is a way to interconnect switches, but the Ethernet standard itself says you will never ever put more than 1,024 computers on a single switch or a bunch of daisy-chained switches. There's reasons for that. First of all, when you're looking at a local area network, there's a lot of stuff going on. Let me show you what I mean. On this particular local area network, I've got 2 computers, A and B. Now, these 2 computers are hooked to 3 different switches. Now, because these switches are daisy-chained together, they pretty much act like one single switch. Now, this works beautifully well until we start adding lots more computers. As we add more and more computers into this, and I'm saying way before we get to that 1,024 computer limit, even with the switches making point-to-point connections, the system becomes horribly overloaded. Heaven forbid you would actually want to connect more than even 1,024. What if you wanted to connect potentially millions of computers together, both wired and wirelessly, and make this thing called the internet? Well, the problem is Ethernet is not going to hack it. The concept of a LAN works fantastic for up to, according to Ethernet standards, up to 1,024, but in reality, 30 to 40 computers is pretty much the standard maximum size for a local area network. We have to come up with some totally different system here. We have to use a system that bases addressing not on the MAC address, but on some other type of address that allows us to, instead of having this one massive LAN, let's make hundreds, thousands, potentially millions of little LANs, and then interconnect them together through something called a wide area network. So let's talk about this a little bit. So here's a 4-computer local area network connected to one switch. I don't care that it's 4, it could be 20 computers for all I care about. In fact, instead of drawing all this out, would it be okay if I just drew a circle? And this circle identifies a local area network. So we're going to call it LAN 1. If we have lots of LANs and we want these guys to be able to intercommunicate, we've got to come up with an addressing system that allows one computer over here in LAN 1 to be able to connect to this local area network over here in LAN 4. So we need some kind of traffic cop, some kind of magic box in the middle that will be connected to our switches, but on the same token, it will be able to go, this piece of data needs to go to LAN 3, or this piece of data needs to go to LAN 2. So we need some kind of magic box. I've got one of these magic boxes right here in front of me. This magic box here in my right hand is called a router. Now, just for comparison's sake, here in my left hand, I have just a regular old, good old 5-port switch, nothing special here. But by looking at them, they seem to be the same, but they are extremely different. Routers are sensitive to different local area networks and can differentiate not between just individual computers, but different LANs. The trick here is that the MAC address allows us to get information to different computers within a LAN, but I need a different numbering system, something else that allows me to identify local area networks. And that's where we get into what we call logical addressing. So if a MAC address is a physical address because it's burned in at the factory, a logical address is something when I buy a computer and I put it in my LAN, I have to type something in to go, this computer is a member of my local area network, and if somebody else goes to the same store and goes to a different LAN, they can type in something to identify their local area network. So there's a value that we type in that identifies us as a particular LAN. Let's talk about how we would go about identifying it. Keep in mind, this is a software function that we can enter, so we can type in anything as long as everybody all across the earth agrees on it. Let's brainstorm. So just for fun, I'm going to call this LAN, LAN A, this one LAN B, this one LAN C, and this one LAN D. The cool part is that we would then go into the router. Let's zoom in on that router a little bit. And just as a switch will memorize the MAC address for individual computers, this router will know this logical address, and we actually will have to punch this into the router. There's a way to configure this. And we're going to tell the router, all the computers plugged in here are going to be part of LAN B. All the computers plugged in here are part of LAN A. All the computers here are LAN D. All these go into LAN C. So let's draw a local area network that most of us know and love. Here's the local area network in our house. So there's usually some box. Now, I know a lot of people call this a router, but for right now, let's pretend like it's a switch. So I've got a laptop over here, and maybe this switch even does wireless stuff. So here's a smartphone over here, and here's your Google Home hockey puck, whatever it is. All of these computers collectively are part of your local area network. The type of logical addressing we use is called IP addressing, and they look something like this. So here's just one example. 192.168.4. Let's just say 100. Every device inside your local area network, whether it's wired or wireless, gets a unique address, which in this particular example, the first three numbers are the same. The last number has to be unique and different. Now, the other cool part is then we also have a router. Now, I'm going to draw the router over here, although again, it's often in this same box. But this router is a member of our network also, and by convention, we tend to give him the .1 address. It's not a law of physics, but that's the most common thing. So the router itself has his own address. So if any two computers want to talk to each other, they don't even really use the IP address. They actually just use their MAC addresses. However, if they want to talk to anybody that doesn't have an address that starts with 192.168.4, they have to send it out to this router. We call this router the default gateway. On the other side of this router is a totally different IP address. I'm just making these up. Because this is a completely separate LAN. This is not our LAN. Here's an example of a typical home router. Now I want you to take a close look at this. This particular one is for cable modem. So it's got my cable modem connection. This is another LAN that's being handled by my cable provider. This guy is wireless, so he can do wireless connections, and he even has a built-in 4-port switch out of convenience. So it's a nice little thing. You don't have to go buy a separate switch. It's all built into this one little device, and it makes our life great. Now, the only trick here is you have to enter this information. Now, I'm going to save actually entering the information for other episodes, but before we part away from WAN, I want to answer one more question, and that is, Mike, I don't think I've ever actually had to type in these 192.168s or any of that stuff. That's right, because built into this device is a special kind of server called DHCP, which we'll cover in detail in other episodes, that when you fire up your computer and you join my wireless network, or you just light up and you're plugged in, it automatically gives you all this information, making our life really, really easy. The big takeaway on this episode, more than anything else, is that every computer on Earth has got two very different addresses. There's a physical or a MAC address, and that's for your local calls as you're just talking to each other. And then you have a logical address based on this numbering system called IP addressing. And I'm going to save all of those for lots of other episodes in other chapters.